Okay, let's talk about how temperature affects chemical reactions. So basically, we know that a reaction speeds up no matter what. A reaction speeds up if you increase the temperature. And in fact, there's an approximate rule of thumb. Again, you'll need to know this for lab. There's an approximate rule of thumb that when you're near room temperature, if you increase the temperature by 10 degrees Celsius, the reaction rate is going to double. Now, this is not exact. It's not always true for all reactions, but it is pretty close for most reactions, okay? So the point here is that when you increase the temperature, the rate of the reaction increases. Now, that means that the rate constant has to increase. Because if you're keeping the concentrations the same and all you're doing is increasing the temperature, that means the rate constant changes. That means the rate constant must increase. Okay, everybody gets that, right? If we're not changing the concentrations and just the temperature, and we can see that the rate law is just the rate is equal to K times the concentration of the reactants, each raised to some individual power. And if we're not changing the concentration of the reactants, that means K must be changing with temperature. Now the question is why? Why is the rate dependent on temperature? Okay. Well, let's illustrate this. We could use a potential energy diagram versus what we're going to say reaction progress. Now, keep in mind, reaction progress is kind of related to time, but it's not. It's going to be called the reaction progress, not time. And it looks like this. So here's a reaction. Basically, we have lost all animation. So basically, we have a potential energy diagram. Here we have the potential energy of the reactants, products, and anything in between. And over here is just the reaction progress. So it's just going in that direction, you know. Again, certain parts could be fast, certain parts could be slow. That's why we don't call it time. But this is what's happening, right? Our reactants, in this case, the nitric oxide and chlorine gas, are reacting to form nitrosyl chloride in the chlorine atom. And we've already said for a reaction to go through that, it has to first go to a reaction intermediate. Now I'm going to be asking you to draw these diagrams from a chemical reaction. The reaction intermediate for us, I'm going to keep it simple. The reaction intermediate is just going to be the reactants, right? So NOCl2, we just put them together as a single molecule, and you put a double dagger beside it as a superscript to the right, okay? That's your double dagger. That indicates that this is the reaction intermediate. So the activation energy, there's a forward reaction, right? That's the reaction going this way. The activation energy is just the difference in energy from where that the top of that peak is for the activated complex to the energy of the initial reactants. So that is our forward activation energy. Okay. But now these products can actually go back. They can go back and reform the reactants. There's nothing stopping them from doing that. As long as the concentrations build up high enough, this reaction will proceed in this way, this direction. And at the same time, mind you, in this direction too. Okay. But going backwards, we're going to have a new activation energy, again, from the peak of the activated complex to the energy of the products. So this time, we have the reverse activation energy, which is only 2 kilojoules per mole in this case. So much smaller than this. This is definitely not to scale, but if I made this 2, you could barely see the down. Now, the enthalpy of a reaction, as we've already seen in Chem 110, is just the difference in potential energy between the products and the reactants. So that's just from here to here. Well, we can calculate that by simply taking the forward activation energy and subtracting the reverse activation energy, which is going to give us the enthalpy. So again, the enthalpy is just the forward activation energy minus the reverse activation energy. So We can see here that the enthalpy is positive. Therefore, this is an endothermic reaction. Endothermic reactions, remember, the reactants gain energy going to products, right? So they're higher. They gained energy going to products. If we had an exothermic reaction, it would look like this. We're going from our reactants, and the products are now lower in energy. That's because the forward activation energy minus the reverse activation energy. And by the way, activation energies are always positive values, right? So activation energies are always positive. You always got to go up over the hump. So they're always positive values. So here we can see this positive value is smaller than this positive value. And again, the forward minus the reverse means we're going to have a negative del H, right? We'll have a negative del H, showing that we have an exothermic reaction, meaning that the reactants lost energy going to the products. Negative del H. Any questions about potential energy diagrams? Okay, now let's talk about this Arrhenius equation. So K. So K is our rate constant, and we can basically say K is composed of three different parts. One, the collision frequency. So that's just the frequency with, the molecules, or let's say we're talking about the gas phase. This kind of applies to the liquid phase as well, okay? But it's slightly different at the liquid phase. So we're going to stay in the gas phase. It's just easier to understand. But so Z is just a collision frequency. How often do the molecules run into one another? Right? So just how often do they run into one another? F is the fraction of collisions with sufficient energy to react, right? So remember, we talked about that before. You have to have that activation energy. So what fraction of the collisions actually have enough energy to get over the activation energy? And then finally, P is the fraction of the collisions that are going to have the proper orientation to react. So these are the three factors that we're going to need to calculate K, the rate constant. Now, the collision frequency is only very slightly dependent on the temperature. So again, if I told you guys to go into a room and start running around, slowly running around, you're all blindfolded, so you're going to all start colliding with one another. But if I ask you to run twice as fast, you're not going to collide with each other twice as much, okay? I mean, you're eventually going to collide into each other with more force, but the frequency with which you collide is actually not going to be much higher than when you were walking around compared to running. So the frequency is only slightly temperature dependent. Remember, temperature is how fast molecules move. So it is a direct analogy having you guys run around and comparing you to molecules that are reacting. And we can see that, right? Because we know, again, the velocity is directly related to the square root of the temperature. So again, the square root of the temperature isn't really, it's not really changing too much how often the collisions occur, okay? Okay, so from kinetic here, we can show that at 10 degrees Celsius, rise in temperature only produces a 2% rise in collision frequency. Now remember, a 10% degree increased the rate by, I guess it would be 100%, right? It would double the rate. So I guess that's an increase of 100%. Okay. So again, this does not account for that. So again, this alone doesn't, very small change due to that. On the other hand, the fraction of molecules with sufficient energy is going to be extremely temperature dependent. So again, we could rearrange it to look like this, that the frequency is equal to E to the negative activation energy divided by RT. So as E increases, F becomes smaller and smaller. But as we increase T, it's the inverse, F becomes larger and larger. So at higher temperatures, we have many more collisions with enough energy to overcome the activation barrier. So we're going to be able to see that we can increase the rate of a reaction by either decreasing the activation energy, and we'll see we're going to use a catalyst to do that, or we're going to increase the temperature. Either one will increase the rate of reaction because it's going to increase the number of molecules that actually have enough energy to react. Okay. And then, so again, I just said that, right? So as the temperature increases, F increases. As the activation energy decreases, F increases. Yeah, I said that. So this is the primary factor that relates temperature to the overall increase in rate that we see for a chemical reaction. Okay. Now, the fraction also depends on the number of molecules that have the right orientation for reaction, and that is completely temperature independent. I mean, it just does not matter how fast you're moving around. That is just random rotation, and you're going to collide with the same fraction no matter what the temperature is. So that is completely temperature independent. So since we already know that P, so the fraction with the correct orientation, and Z, the collision frequency, are both basically temperature independent, we're going to combine them together and make that a single constant, which we're going to call A. Okay, so A is known as the pre-exponential factor or the collision frequency. It's known as a lot of things, but generally we call it the pre-exponential factor because it does include both the collision frequency and the orientation. So again, you might sometimes hear it referred to as the collision frequency, but the reality is it contains both the collision frequency and the value needed for proper orientation. So we call that the pre-exponential factor. And this is what we call the Arrhenius equation. So we can see K then is dependent on the frequency factor, which isn't going to change with temperature, the activation energy, and then the temperature. And R, of course, is just a molar gas constant. That's going to be the 8.3145 joules per Kelvin per mole. Now, we could also rewrite this in logarithmic form. So in other words, we can get rid of the E part here by simply taking the ln of both sides. So we're going to have the ln of K, we'll have the ln of A, and then when we have the ln of E to this, it's actually just negative EA over T. And so that's where that comes from, the negative EA over ln of T. So we just did it by simply taking E to both sides. That got rid of the E, okay? I'm sorry, we took the ln of both sides, which got rid of the E. Okay, so now we can relate this again in the form of a straight line, right? So there's your Y, there's your intercept this time, and then your slope is negative EA over R, and your X value is going to be plotted 1 over the temperature. So this is, again, is another real easy way to determine the activation energy. And for those of you who have lab, you'll do this. You're going to plot this, and you're going to find the activation energy of your reaction. Okay. Okay. Now, again, I just said that. Okay, so let's try to determine then the activation energy of an experiment. So we ran an experiment at a bunch of different temperatures, and we determined the rate constant at each one of those temperatures. And then we're going to plot it, right? We're going to plot it. So the ln of K, okay, so we're going to take the ln of this value and plot it on the y-axis. And then we're going to plot that as 1 over the temperature, so the inverse of the temperature. So it's going to be 1 over the 45, 1 over the 50, and we're going to plot that on the x-axis. That's going to give us a straight line. Again, just use the trend line, linear regression in Excel, That's going to give you a line, and it's going to give you the y equals mx plus b equation. And therefore, the slope, as we've already seen, is actually negative EA over R. So EA is just negative R times the slope. Okay. Okay, any questions about the Arrhenius equation so far? Okay, now the Arrhenius equation is also very helpful. We're going to modify it in a little bit, in a little bit here, as you'll see, and we're going to be able to determine rate constants at any temperature if we know the activation energy and the rate constant at any one temperature. Or we'll be able to determine the activation energy if we know the rate constant at two different temperatures. Okay, so basically we're going to do it like this. Let's say we have the rate constant at two different temperatures, right? Here's the one, and here's the other one at another temperature. If I take these two equations and subtract one from the other, I'm going to get something that looks like this. Now, the ln of A cancels, right? Because it's the ln of A minus the ln of A. Since it's temperature independent, it's not changing, and so that's why it disappeared. And then doing some rearranging in properties of logs, we end up with this equation here, which we call the modified Arrhenius equation. Okay, this is actually a very helpful equation. So there's the modified Arrhenius equation. And like I said, we're going to be able to use this. If we know the rate constant at two different temperatures, we could find the activation energy. Or if we know the activation energy and the rate constant at any one given temperature, we can now determine the rate constant at any other temperature. So we could use the modified Arrhenius equation to do that. Okay. Okay, let's try an example then. So the rate constant for the formation of hydrogen iodide from its elements, hydrogen and iodine, is 2.7 times 10 to the negative 4 liters per mole per second at 600 Kelvin, and 3.5 times 10 to the negative 3 liters per mole per second at 650 Kelvin. Determine the activation energy of this reaction. Okay, so we're going to use the modified Arrhenius equation, and in this case, we're going to be solving for the activation energy. These temperatures have to be in Kelvin. First off, this is 8.345 joules per Kelvin per mole, but I didn't go through it, but this also has the ideal gas equation is also used in part of its derivation. So therefore, you have to use temperature in the absolute scale. Okay. Okay, so we're just going to plug and chug, right? We know the rate constant, which we'll call K1 at 600K. So there's K1, and then our T1, which would be 600K. And then our second one, this is K2, right? So K2 or K2. And then that temperature was 650. So for K2, it's T2. So T2 is 650. And again, the R is just the 8.3145 joules per Kelvin per mole. Now keep in mind, EA's units are given in kilojoules per mole. Okay, so they're always given in kilojoules per mole. So we're going to solve this then, right? So we just took this divided by that, and then this number over here, that's the intermediate steps. Take the ln of that, that gives you the 2.56. Do a little bit of rearranging, and EA is then equal to this. We can see the per Kelvins cancel. We're left with joules per mole. That's exactly what we would expect for an activation energy. But again, like I said, activation energies are generally given in kilojoules per mole. So this would be 166 kilojoules per mole. So that would be the forward activation energy for this reaction. Okay. Okay, any questions about that? So this is number 38. It says nitric oxide. Okay, so nitric oxide causes the decomposition of ozone to form nitrogen dioxide and molecular oxygen. So this is bad NO, which is produced in exhaust of cars that don't have their catalytic converter, migrates to the upper atmosphere and converts the ozone back to regular oxygen, And then all of a sudden, more and more UV light is allowed to penetrate down to Earth, which is bad for us, bad for animals, bad for everything else, but who cares? Okay, so given the activation energy for the forward reaction, okay, so activation energy, forward reaction. So I know that activation forward is equal to 10.5 kilojoules. And the enthalpy is equal to negative 200.8 kilojoules. I want to know, what is the activation energy for the reverse reaction? So how am I going to determine the activation energy for the reverse reaction?
Plug and chug.
Okay, but what equation?
Delta H equals EA forward minus EA reverse.
Exactly, right? We know that the enthalpy is actually equal to the forward activation energy minus the reverse activation energy. So we're just going to we're going to bring this over and then subtract this from this side. So that means that EA forward minus del H is going to equal our reverse activation energy. So then that's going to be, the forward was 10.5 kilojoules. We'll subtract from that the negative 200.8 kilojoules. And that is going to give us a value then of 211.3 kilojoules. Now this was one pass, this was one pass, so this is one pass, so that is the actual answer. Okay. Okay, what if I would have came up with a negative 211.3? Would that make sense? Is that, why not?
You can't have it. You can't have a negative activation energy.
Exactly, right? You can't have a negative activation energy. Del H can be negative or positive. It could be negative is exothermic, positive is endothermic. But you can never have a negative activation energy. It's always going to be an increase in energy. So that takes us to the second part of this. It says, sketch the appropriately labeled potential energy diagram. And usually I'll tell you what I want to see, okay? But I always want to see it. Even if I don't specifically say it, I'm telling you, I want to see everything that I'm about to write. Okay, so potential energy diagram. So basically we have something that looks like this. What's going to be on the y-axis?
Energy.
Energy, right? And specifically, it's actually potential energy. So we're going to put energy over here, and that's going to be in kilojoules. You can put E or write out the word energy. I don't care. And then what about the x-axis? What do we label it? I have a question. Is there can you see a little camera where my mouse is right now? You don't? Okay, that's good. So you don't see all the crap that I'm seeing on my screen. So what's going to go on the x-axis then? For a potential energy diagram.
The reaction process.
Say that again. The reaction.
Progress.
Progress, right? So we can call this reaction progress. You could also call it the reaction coordinate, okay? So either reaction progress or progress of reaction, reaction progress, reaction coordinate, not time, okay? Not time, definitely not temperature, okay? But not time. Okay, so what shape am I going to give this? And it does not have to be to scale. So this is going to be the potential energy of like the reactants and the products, right? But should the reactants and products be put at the same energy? No. How should I put them then? Which one should be higher in energy, the reactants or the products? What happened to the reaction and products during this reaction? Did the reactants gain or lose energy? Did they gain or lose energy?
They lose energy.
They lose energy. So should I put the reactants higher than the products, or the products higher than the reactants?
Reactants higher than the products.
Yeah, right, because it's going to lose energy. We're going to start here with our reactants. In this case, it's NO and O3, right? So NO and O3, there's our reactants. And then our products are going to be lower in energy, which is our NO2 and our O2. And then what do I need to complete this graph, this drawing? What should it look like? Just go straight from here to here? Well, it's actually going to have a hump, right? It's going to go like this. There's going to be a hump. And what do we call this? What is this hump?
The activation energy.
Yeah. Okay. In fact, there's two activation energies, right? There's a forward activation energy. So in other words, I'm going from here up over this hump. So that activation energy then is this right here. This is my forward activation energy. And we know that it is this 10.5 kilojoules, right? So 10.5 kilojoules. But we also have a reverse, right? If we're going this way, we got to overcome this amount of energy. And this is the reverse activation energy at, we just calculated 211.3 kilojoules. What happens at this point? So I know at the reactants, this is what I have. When it finally gets to the products, this is what I have. But what's happening here in the middle? What's happening here at the middle? Well, remember, right? What's literally happening on a molecular scale? These two guys are colliding with one another, and then they start to form bonds and break bonds. And so I have this. Now you could write this however you want. I'm just going to write it like this. So it's NOO3. What do we call that? What is NOO3?
Wouldn't that just be the activated complex?
Absolutely. And how do I represent an activated complex? Do I have to add anything to this?
Do you have to put a plus and minus?
No, it's a double dagger. It looks like that. That's called a double dagger. And that is telling us that this is our activated complex. Okay. How would I represent the enthalpy on this diagram? How would I represent the enthalpy? Well, remember, the enthalpy is just the difference in energy of what?
The difference between the reactants and products.
Exactly, right? So if this is the energy of the products and this is the energy of the reactants, this is the enthalpy change. Right? So you can see how del H is related. If this is the forward activation energy and this is the reverse activation energy, if we just subtract off that hump, right? So we take the forward minus the reverse, and that gives us this value here. Okay, so that's everything that I would want to see if I ask you to draw a potential energy diagram on an exam. Any questions about any of that good stuff? Okay, let's try one more problem then before we get back into the lecture slides. This is number 42 out of chapter 14. And it says nitrosyl chloride is a toxic yellow gas used in the synthesis of a variety of organic compounds. It slowly decomposes to nitric oxide and chlorine gas at elevated temperatures. It wants us to calculate the activation energy, right? So the activation energy is EA for this reaction, given that the rate constant, so that means this is K. So K is 9.3 times 10 to the negative 5. And then there's a temperature at 375 Kelvin. Oh, but wait a minute, it's given us a second rate constant. So we're going to call this K1, and this must be T1. So therefore, this is K2, and at that temperature, T2. We'll come to the second part later, okay? So it's asking us to calculate the activation energy for this reaction, given that the rate constants were determined, 6.3 times 10 to the negative 5 per second at 375 Kelvin, and 8.1 times 10 to the negative 2 per second at 475 Kelvin. So given that information, how am I going to determine the activation energy?
The modified Arrhenius equation?
Yeah, the modified Arrhenius equation. What does that look like?
Log with, so ln.
So yeah, the natural log.
Yeah, K2 over K1 equals EA over R, and then 1 over T1 minus 1 over T2.
Absolutely. Okay. And we're solving then for EA.
Mm-hmm.
Now, again, you could rearrange this whole equation or you could solve it piecemeal, whichever way you like. Again, I'm going to rearrange it. So to isolate EA, I'm going to multiply both sides by R. So in other words, I'm going to take it from the denominator on one side to the numerator on the other side. So that's going to be R, the ln of K2 over K1. And I'm going to divide by this quantity. So I'm going to divide the whole thing by 1 over T1 minus 1 over T2. Now, again, I can plug it all into my calculator as one big thing. Avoid any rounding errors, transcription errors, any of that kind of stuff. Okay. What's the value of R? Leah, what R are we going to use here?
Zero 0.082058.
And what are the units of that?
Atmosphere per liter per Kelvin
Kelvin per mole.
per mole.
Does that make sense? What
Wait.
units do you expect for EA?
Joules.
Oh yeah. Okay, so
So
you're gonna use the 8 point. Is it 0?
yeah, the 8.3145. And what are its units?
And that are those in joules?
Joules and
Per Kel. Is it per Kelvin? Yeah, per Kelvin.
is that right?
I think so.
I hope so.
I hope so too.
Okay, so then the ln of K2, well, we said K2 was this value, right? So that's 8.1 times 10 to the negative 2 per second. Divided by K1, well, we said this is K1, so 9.3 times 10 to the negative 5 per second. And then we got to divide this by 1 over T1. Does it matter what units T is in?
T should be in Kelvin.
Why?
It cancels out with the units of R.
Absolutely right. So it cancels out with the units of R. There's actually another reason. The ideal gas law is used in the derivation of this equation. We won't go into it. It's really complicated. I take thermodynamics, Chem 452, or no, 450, and you'll learn about that derivation. You'll see it's not fun. But the idea is that these got to be in Kelvin. Number one, to cancel those units, but again, because it's derived from the ideal gas law, you're going to have to use Kelvin anyway. So again, we have T1. So T1 was 375 Kelvin. And then we have T2, which is 475 Kelvin. Now, as far as units are concerned, well, this is going to cancel. Now think about it. This here is going to end up being, this portion here is going to end up being 0.0005614. It's going to end up being the 2 sig figs whenever you do everything that you need to do. And what are the units going to be? So I'm just doing this denominator part here, just the denominator. Ignore the rest of it, just doing the denominator. What are the units going to be after I take this minus this? Well, it would be 1 over Kelvin, right? And we would say per Kelvin, because that's what that means, right? 1 over Kelvin would be per Kelvin. So we did this intermediate step here, so that's what that equaled. Now we can see that the per Kelvin cancels the per Kelvin. And we're going to end up with units of joules per mole, exactly what I would expect for an activation energy. Okay. Any questions with that good stuff? Okay, so we'll plug that into our calculator, and we are going to get 1.0026 times 10 to the 5th joules per mole. Let's see, we have 5 sig figs, 2 sig fig, 2, so this is going to be 2 sig figs. So in the end, we'll say it's 1.0. I'm actually going to change this to kilojoules because that's the normal units. So to change it to kilojoules, right, we're going to say, well, this is joules. Well, there's 1,000 joules in 1 kilojoule. So that's 10 to the 3rd, 10 to the 5th. So that means this is going to be times 10 to the 2 kilojoules per mole. So there is the activation energy for this reaction. Any questions with that? Okay, now what about this second part? Now I want to know what the rate constant is at 425 Kelvin. How am I going to solve that? What concept, idea, equation, what am I going to do to solve this? I want the rate constant at 425 Kelvin.
You rearrange the modified Arrhenius equation to find the rate constant.
Yeah, right. I'm just going to use this equation again. Right? Now I know EA, and I could use either the K1T1 set or the K2 T2 set. It doesn't matter which one you use. Okay, now we want to solve for K. So in this equation, which K do you think is easier to solve for mathematically? You think K1 or K2 is easier to solve for mathematically?
K2 is easier.
Yeah, K2 is going to actually be easier to solve for, because I'm going to get rid of this, and then I'm going to multiply this to this side, right? So again, to get rid of this, I got to raise both sides to the E. So that means we're going to have E to the EA over R, 1 over T1 minus 1 over T2, right? Now that gets rid of that. Now I have K2 over K1, so I just multiply both sides by K1, and there's the equation for K2. Now, which variable do you think is easy to solve for if I gave you a rate constant and asked you to solve for one of these T's? Which T do you think would actually be easier to solve for? T1 or T2? Think about rearranging it, right? Which one do you think is going to be easier to solve for?
T1.
T1, absolutely, right? Again, I want to solve for T1. So I got to isolate it. So I'm going to multiply both sides by R and divide by EA. So that's going to give me R, the ln of K2 over K1, divided by our EA, right? So now I have T1 minus T2 on this side. So I'm going to add 1 over T2, and that's going to give me 1 over T1. Now, this is the way I would solve it. I would actually plug this, because then to take the inverse of both sides, now all of a sudden that would put this whole thing over 1, and now T1 would equal all of that nonsense. So I would actually just solve for 1 over T1, wouldn't do any of that. This would be a 1, and I would solve the equation this, and then finally take the inverse of whatever that answer is, which would give me T1. Okay, so think about what variables are easiest to solve for when you're doing these types of problems. Okay, so coming back to this, I'm just going to use the K1 and the T1, right? And it'll be K2 that we're solving for at 425. So K1 was given to us as 9.3 times 10 to the negative 5 per second. Then we have E raised to the EA. Now, I'm not going to use this one here because I know that the R value is 8.3145 joules per Kelvin per mole. I should have did this on the next line down. So I'm going to use this EA value, so 1.0. And again, I'm not going to use a rounded value if I have the unrounded value. Okay. So there's that. And then we got to multiply it by this here. So we're going to multiply this. So we're going to multiply this entire thing by 1 over T1. T1 was our 375 Kelvin. And now I'm going to subtract from that, oh, this is bad, 1 over our new temperature of 425 Kelvin. Okay. So again, remember, this is going to end up being per Kelvin, and there's a per Kelvin. So the kelvins are all going to cancel. My joules are going to cancel. My per moles are going to cancel. That's good because this needs to be a unitless number. Again, you'll avoid a lot of math mistakes if you use your units. Okay, and it doesn't take any time to do that. So now I can just plug this into my calculator. So this is going to be what, 9.3 times 10 to the negative 5 per second times this whole value, and then to the E is going to be 43.9496, and it's unitless. And this was 2 sig figs. This thing's, after you do all of the stuff, is going to end up being just 1 sig fig in the end. And this is going to be unitless, and then plug that into your calculator, and you're going to get 0.00487 per second. Again, it's only to 1 sig fig. So it's going to be 4 times 10 to the -3 per second. Okay, any questions about that?